Hello. So in this video, we're going to be looking at some problems from this great book, which I absolutely love and will probably be doing more videos on as well. It's called The Art and Craft of Problem Solving by Paul Zeitz. Now here we're going to be looking at this chapter on the extreme principle, and we're going to be looking at some of the problems there, and I'm going to try and show you my thought process in solving one of these. So I think I've looked at some of them, and some of them are pretty simple. But let's maybe try some of the later ones. Here, this one, part of a tournament, Canada 1987. Let's try this one. Okay, I'm just gonna grab a quick capture of this. And bring this over here. Okay, now I have this right here for me. Okay, here's the problem. On a large flat field, n people, n being more than one, are positioned so that for each person, the distance to all other people are different. Each person holds a water pistol, and at a given signal fires and hits the person who is closest. When n is odd, show that there is at least one person left dry. Is this always true when n is even? Okay, just immediately looking at is this true when n is even, I would say no. Because if you just have a pair of two people, they'll shoot each other. Now they probably also want some idea about which ones are true when n is even and which ones are not. But for now, I'm just going to focus on this other one. When n is odd, show that there's at least one person left dry. Now I think actually one thing might slightly change. And actually I don't know if this is what they may have initially intended, but I'm going to say that so when it says for each person the distances to all other people are different, I'm going to say every single distance to every other between pairs are different. They're all distinct. Okay, so I'm going to go with that. So now, the first thing you should always do, and that I always like doing when I approach a new problem, is to just get your hands dirty a bit. Try out some different values. So maybe let's try 3 and 5. Those are the next odd numbers. So let's do 3. So let's say we have 3 people here. So see, this person shoot here. Yeah. And this guy will also shoot back. And then this guy will shoot, I don't know. They both look pretty close. That one. Okay. So that one I can see, yes, this person is left dry. Now, let's do with 5 people instead. 1, 2, 3, 4, and 5. Let's see. This person looks like they're definitely gonna shoot here. Yeah. This person, I think it's close, but I think they're just gonna shoot back to this guy. This person is gonna shoot here, obviously. And I think these two may just shoot each other. So I'm noticing that straight off the bat, there are these pairs that are forming. Like these two are paired up and these two are paired up, always leaving this one guy blank. That's giving me some idea here that maybe you should look at the pair. Now, obviously, like I said before, this problem looks at the extremal principle. So you want to look at a maximum or minimum value. And even if you didn't have to know the fact that it's an extremal principle problem, whenever you have a large set of things, or just any amount of any set of things, you want to look at the maximum or the minimum, because those could always simplify it for you. So here, I don't think the maximum may give you some help, but my initial thinking is I'm going to use the minimum somehow, because obviously that for the minimum, that I think about it, because all the numbers are distinct. Since there's a minimum distance, they're both going to shoot each other. And I think the minimum distance is these two right now, and in this case also these two. So I'm thinking, right now, they'll shoot each other. And then, how can we... So can we kind of just get rid of them? Because actually, one thing I'm noticing is, see, right now we have so that this guy is shooting at him, doubling up on him. But remember that there's a 1-to-1 ratio between people and guns. Therefore, if everyone has to be shot, then every person has to be shot exactly once because there's the same amount of gunshots as there are people, so everyone has to be shot once. So if someone, like in this case, is shot twice, then we immediately know that one person is therefore not shot at all. So when we look in this minimum pair, if someone else shoots at this pair, it's gone. It's completely gone. Then we have our proof, technically. We already have it. So let's look at a case when that's not the case. Let's take this guy, move him maybe closer here, so that now it's closer to this person. But now I'm noticing that these people are just completely separate. They're a whole separate box. So what if we just take these away? I'm noticing now we have a position of 3. We have a lower odd number where we can do the same pairing up thing. So now that's giving me an idea for a proof. And I think that basically solves it, because with any odd number, you just pair them up. If that pair is shot at, then one person shot twice. Therefore, some person is also not shot at all. And then also, if that pair is not shot at all, you remove them and you have a smaller odd number. And you're going to keep doing that until you get down to 3 people where that other person has to shoot the pair. And in that case, that other person will not be shot at all. So I think we've just proved that when n is odd, there's at least one person always left dry. So we've proved that. Now, one thing I want to do, and one thing that's good for you all to practice is, even though I've kind of got a solution here, you want to be able to write a proof of it. So I'm again immediately thinking of some sort of induction, because I'm thinking like I had this larger odd number and I was able to bring it down to a smaller odd number. So I'm able to do something like that, going down incrementally. I immediately think induction. If you don't know what induction is, you could try to learn it through this, or I would suggest looking up some videos on it, or put it down in the comments and I'll do a video on it. But anyway, let's try to write a proof out. Sorry, my throat's hurting a bit. That's why my voice is a bit croaky. So let's do a proof. So first, because of induction, we're going to start with a base case. So let's start with a base case. It'll be 3 of 3 people, since n is always larger than 1. So of 3 people. So again, there will be a minimal distance pair, I guess you could say. And this pair will shoot at each other. Actually, one thing I want to do is I'm going to start off this proof by giving our noticing of this 1-to-1 ratio. Notice that there are equal guns. There are an equal amount of guns as there are people. Hence, if every person is to be shot, every gun is to be used on a different person. So therefore, it's enough to prove that at least one person will be shot twice. Okay, so let's start with the base case of 3 people. There'll be a minimum distance pair. Minimally distance pair. And this pair will shoot at each other. Okay. Then the third person will shoot at one of these 2 again. Thus, one person will be shot twice. Yeah, okay, that makes sense. Now we're gonna do the induction hypothesis step, which is kind of just saying, assume that one person is left dry for n people. Can we do italics? No, it's fine. N people. We just need to prove that it's true for n plus 2 people, since we're incrementing by every odd number. So again, let's look at the minimally distanced pair. This pair will shoot at each other. If another person shoots at this pair, then one of them is shot twice and the theorem is proved. So assume that they're not shot at all by others. Then we can just exclude them, and focus on the remaining people. We are left with n plus 2 minus 2, which equals n people. Using the induction hypothesis, we know that one of these people are going to be left dry. QED. So that's it. So look, down the basics of this. What have we learned from this? So first, we just played around with some cases, 3 and 5 people, and we noticed something with pairs. And then because we had a set of things, we looked at the minimum value using the extremal principle, and we noticed that if they're shot at, then we know someone won't be shot because someone shot twice. And if they're not shot at, we notice that they're completely isolated from this group. So we have a smaller case. And when I'm able to transfer like this, I immediately think of induction. And we see how it's proved nicely right here. Thank you for watching, and keep on problem solving.